Welcome to Pure Process, a journey into some of the most remarkable mechanical processes ever developed through traditional craft. Today, we follow Joseph Schneider to Meisburg, a small village in the quiet Eifel region, where a water-powered sawmill still operates much as it did centuries ago. This is not only the story of a machine, but of a lasting relationship between human skill, natural force, and mechanical engineering. Some people never leave the place where they were born, not because they are unable to go elsewhere, but because their entire lives remain tied to something that endures. Joseph Schneider was born in 1923, and nearly his whole life unfolded within the Schneider Sawmill, a modest timber structure on the outskirts of Meisburg, where he continued working until 1968. Meisburg is a small village with only a few hundred residents. Set in the quiet Eifel region, its distance from modern industrial life has allowed many traditional technical structures to survive in everyday use. The Schneider Sawmill stands at the center of the village as a functioning heritage site, not preserved as a static monument, but as a working mechanical system. The structure remains largely intact and still operates according to its original mechanism. It is among the very few historic water-powered sawmills that remain practically usable. When school groups come to visit, they do not encounter only an old building, but a living witness to the passage of time and to the continuity of technical knowledge.
Für wen von euch wird das heute der erste Besuch einer Schneidemühle sein? Oh, das ist überraschend. Gab es in euren Heimatdörfern keine Mühlen? Bitte? Ja. In Pützborn auch?
Ja.
Was erinnert denn noch in Pützborn an eine Mühle?
Alte Mühlgraben.
Ah ja, wo ist der denn? Da, parallel zum Pützbach wohl.
Parallel zum Bach.
Wo verläuft der?
Ja, der Bach, der ist gestaut zwischen Pützborn und Neunkirchen. Und von da ab läuft dann der Mühlgraben bis zur Bundesstraße.
Moin, Herr Schneider. Guten Morgen. Schön, dass Sie uns die Führung machen.
Ja, auch herzlich willkommen.
Und wenn ihr zusammen seid, könnt ihr auch den Herrn Schneider begrüßen.
Ja.
Each week, Joseph Schneider returns to the mill to maintain the timber structure, recondition the saw blades, and receive visitors. The operation begins with the regulation of water flow. Before any cutting starts, the energy source of the system must be stabilized and brought under control.
Und jetzt kommen Sie bitte mit, sehen wir uns zuerst den Mühlgraben an. Ja. So,
Geht die los?
kommen Sie nur näher an.
Sascha, du kannst was ordentlich. Ja.
So, hier befinden wir uns jetzt an unserem sogenannten Mühlgraben, der aus dem Losalenbach abgeleitet wird. Um die Säge in Betrieb zu setzen, wird nachher diese Schleuse mit dem Seilzug hier betätigt, beziehungsweise der Zulauf des Wassers reguliert, je nach Bedarf, um die richtige Kraft zu erzeugen. Sollten Sie jetzt irgendwelche Fragen haben, ich möchte sie gern beantworten.
Ja, wie alt ist der Wassergraben hier?
Ich kann nur sagen, hier soll 1346 die erste Mühle gestanden haben. Mithin müsste auch so alt sein.
Wie lang ist der Mühlengraben?
Der Mühlgraben ist 350 Meter lang.
Wie groß ist der Höhenunterschied zwischen Bach und Mühlengraben?
Der Höhenunterschied ist gut 7 Meter, weil das Wasserrad hat ja einen Durchmesser von 6,70 Meter.
Der Mühlgraben, wie wurde der ausgegraben?
Der Mühlgraben wurde praktisch in Handarbeit ausgegraben.
When school groups come to visit, Joseph shows clear pride in his sawmill. He eagerly explains the system to the students, guiding them through each part of the process. For him, this sawmill is a source of pride, and perhaps he hopes that the younger generation will one day develop these machines further into more advanced systems.
So, hier sehen wir jetzt unser Wasserrad in natürlicher Größe. Hat einen Durchmesser von 6,70 Meter, bringt eine Leistung von 15 PS, ist gebaut worden in den Jahren zwischen 1930 und 40 und läuft bei uns hier seit 1950. Und bis 1950 war es ein Holzrad.
Wie viele Schaufeln hatte das Wasserrad?
Das Wasserrad hat 62 Schaufeln.
Ja, wie wurde die denn zusammengebaut? Wurde die hier direkt an Ort und Stelle zusammengebaut oder wurde die so geliefert?
Dieses Rad war in 8 Teile zerlegt und wurde dann hier an Ort und Stelle wieder zusammengebaut.
Die mechanischen Vorgänge werden zur Verdeutlichung nun nacheinander geschildert. Sicherheitsabsperrung und Plattform.
In front of the structure, a spillway diverts excess water away from the system, ensuring a stable supply to the water wheel.
Überschüssige Wasser ableitet. Per Seilzug öffnet und schließt der Sägewerker vom Gatter
The
aus
sluice gate
den
is
Schieber
operated
des
by a
Wehrs.
rope pull mechanism, allowing the operator to control the volume of water entering the system directly from the saw frame. From there, the water runs along a gently sloped head race, passes beneath the working floor and saw platform, and then pours into the buckets of the water wheel. The sawmill uses a breast-shot water wheel, weighing approximately 3.5 tons. Water from the elevated head race enters the buckets and sets the wheel into slow, steady rotation at a maximum speed of about 10 revolutions per minute. Each full revolution produces 18 strokes of the saw blade, corresponding to roughly 180 vertical motions per minute under optimal conditions. The wheel's efficiency is estimated at around 80%. According to Joseph Schneider's own calculations, with well-maintained bearings and mechanisms, actual efficiency can reach as high as 95%, delivering an output of approximately 15 horsepower. The rotational motion generated by the wheel is then transmitted into the drive system of the sawmill. The wheel is connected to the main shaft, which drives a large gear wheel approximately 3 meters in diameter. Motion then passes through a smaller pinion and a transmission shaft to the belt pulley on the right, supplying mechanical power to the sawing system. From the driven pulley, motion is transferred through a system of flat belts that directly power the saw assembly. Transmission efficiency depends on the balance of the wooden pulleys and the condition of the bearings. A return belt is used to pull the log carriage back out of the saw frame. Directly beneath the frame, a clutch mechanism allows the operator to shift the belt from an idler pulley to a drive pulley, enabling controlled engagement and disengagement of the transmission. Rotary motion is then transmitted to the saw shaft. Connecting rods mounted on the crank wheels at both ends of the shaft convert rotation into the vertical reciprocating motion of the saw frame, creating the characteristic rhythm of a water-powered sawmill. Once the frame is running steadily, the log feed mechanism is engaged. A steel cable running over a winding drum advances the log carriage step by step toward the saw blade, synchronized with the downward stroke of the saw. During operation, the connecting rods and other moving components are shielded on both sides of the saw frame for safety. The control mechanisms are routed upward to the working platform, allowing the operator to monitor and regulate the sawing process directly. The Meisberg sawmill clearly illustrates the technological evolution of traditional water-powered sawing. When Joseph Schneider's father took over the mill in 1922, the system still operated with a single connecting rod and a single saw blade. Later, a double connecting rod saw frame, based on designs once used in the sawmills of Himrod Abbey, was installed. And Joseph Schneider added a second blade. These modifications followed a broader European movement toward multi-blade sawing systems that had already emerged in the late 16th century. Their purpose was simple: to improve efficiency without abandoning the mechanical principles that made water-powered sawing stable, durable, and reliable. These improvements were not isolated changes, but part of a wider shift in European woodworking. From the late 16th century onward, sawmills gradually moved toward multi-blade systems, increasing output while still relying on the same core principle of water-driven motion. Efficiency was improved, but the structure of the machine remained grounded in mechanical simplicity. Inside the mill, the operator can position two smaller logs side by side on the carriage and process them simultaneously within a single saw frame. Alternatively, a single large trunk, sometimes reaching a diameter of nearly 1 meter, can be cut alone. Under normal conditions, each pass takes around 10 minutes, although hardwoods such as oak require more time due to their density and the reduced feed speed needed to maintain stability. After each cut, the carriage is pulled back along its guide rails using a steel cable. The log is then advanced forward by a fixed increment, corresponding precisely to the thickness of the next board. This step must be repeated with accuracy, as even a small deviation would affect the uniformity of the final material. Instead of using calibrated measuring instruments, positioning relies on simple mechanical references. Two nails are used as fixed points, one driven into the log and the other into the carriage. By aligning these markers, the operator can set the cutting position with reliable precision. Board thickness is further controlled using wooden gauge sticks placed directly against the saw blade, each representing a standard dimension for repeated cuts. The forward and return movement of the carriage is controlled through a ratchet and pull system. As the carriage moves toward the saw, a cable winch rotates through a gear train. A drive pole engages the ratchet wheel, converting continuous rotary motion into step-by-step advancement. This movement is carefully synchronized with the downward stroke of the saw frame, ensuring that the cutting action remains stable and controlled. To stop the mill, the operator first shuts off the water supply. Without incoming flow, the wheel gradually slows and comes to a complete stop. The drive pole is then disengaged and a floor-mounted lever is shifted to idle, disconnecting the feed mechanism from the rest of the system. When operation resumes, water is released back into the head race. The wheel begins rotating again, and motion is transmitted through the drive system into the saw frame. Only after the system reaches a stable rhythm is the feed mechanism re-engaged, ensuring that cutting begins under controlled conditions. During the 19th century, water-powered sawmills were widely distributed across the Rhine region. In 1846, records show that as many as 98 sawmills were operating in the Trier administrative district alone. These installations formed an essential part of regional industry, supplying timber for construction and trade. Technically, most sawmills followed either the German or Dutch configuration, each adapted to local conditions. Circular saws were introduced in the early 19th century, but they accounted for only a small fraction of installations, around 10%. Traditional frame saw systems remained dominant due to their reliability and suitability for available power sources. The operator of a water-powered sawmill was not simply a machine user, but a skilled craftsman responsible for both production and maintenance. Drive belts required constant adjustment, and damaged wooden gear teeth had to be reshaped and replaced by hand. Every component demanded attention. In dry conditions, the timber structure of the machine could shrink, causing gear teeth to loosen and produce vibration or noise. These signs indicated the need for immediate correction. At the end of a cut, if a board remained partially attached, it would be separated manually using an axe to complete the process. The Meeburg sawmill is well preserved through long-term heritage restoration. Joseph and Josephine Schneider are supported by the State Heritage Authority in Mines, the District Administration, and the Dawn Municipal Association in maintaining this technical monument. Among all components, the wooden drive gear teeth and the frame saw blade experience the highest level of wear. After approximately 12 to 15 cutting cycles, the blade must be sharpened again using a rounded edge file designed specifically for this purpose. This process restores the cutting efficiency and ensures that the blade continues to move smoothly through the timber without excessive resistance. In modern configurations, the saw teeth are alternately set to the left and right, stabilizing the cutting path and preventing the blade from binding. In earlier practice, however, an intermediate tooth setting closer to the center line of the blade was often used. This method improved the removal of sawdust under traditional operating conditions, especially when working with slower mechanical systems. The sawmill extends beyond the cutting frame itself. From the main structure, timber guide beams reach outward toward the log yard, where raw wood is stored and prepared. This layout allows material to move continuously from storage to processing without unnecessary handling. Joseph Schneider learned the craft through direct experience, observing and assisting his father from an early age. Even before the Second World War, he worked in the mill while still attending school. After the war, he assumed full responsibility for operations, managing the sawmill with a workforce of around 12 people until the mid-1960s. After that period, the system was maintained largely through his own labor, supported by his wife. The operation of the sawmill depended entirely on water availability. During periods of drought in summer, reduced flow required water to be stored in advance in order to maintain operation. When urgent work needed to be completed, Schneider and his family would continue working through the night, even while the younger members were still attending school, until the head race finally ran dry. In winter, ice formation on the waterwheel slowed its movement and could bring production to a complete stop. This reliance on natural water conditions was both the system's greatest strength and its most significant limitation. The mill functioned in direct relationship with the environment, not independent of it. At first glance, the sawmill appears to be nothing more than a simple wooden structure set within a rural landscape. However, a closer examination reveals a complete technical system where human skill, natural forces, and mechanical elements operate together in mutual dependence. Every gear, every belt, and every movement reflects knowledge accumulated over generations. The life of Joseph Schneider forms the central thread running through this system. He was not merely the operator of the machine, but its caretaker. Measurements of efficiency or output only gain meaning when tied to someone who understands the limits of materials, listens to the sound of the machine, and senses changes in water flow across the season. The Meisberg sawmill represents a fundamentally different approach to engineering. Rather than maximizing speed or output, the system is designed for stability, precision, and adaptation to natural conditions. The slow rotation of the water wheel is not a weakness, but a deliberate choice that reduces wear and extends the life of the entire mechanism. In a broader historical context, the sawmill stands as a representative of a once dense network of water-powered systems along the Rhine region. These mills provided essential materials for construction and formed a key part of rural economies. With industrialization, most of these systems disappeared, leaving only a few surviving examples. Today, as interest in sustainable energy returns, water-powered systems are once again being studied and restored. In this context, the sawmill serves as a reminder that renewable energy is not a new invention, but knowledge that has existed for centuries. Here, water is not forced, but regulated in balance with human labor and environmental conditions. Preserving the sawmill means more than maintaining an old structure. It represents the preservation of a way of thinking, a culture of work, and a shared technical memory. These systems embody a form of knowledge that cannot be separated from the people who operate them. As long as the water wheel continues to turn slowly and steadily, it carries forward the story of a time when technology, nature, and human experience were closely connected. In that system, lasting value was not defined by speed, but by endurance, balance, and understanding passed down through generations. If you find value in processes like this, you can follow pure process to discover more systems shaped by precision, patience, and experience. Until next time.